relation. So it is a BSc third year 6th semester elective paper. So today we are going to discuss recurrence relations. So this is totally 60-minute session. So 40 minutes there are two experts will be there and will discuss about the recurrence relation, and the remaining 20 minutes are there is interact with the viewers or students through the telephone numbers. So you can contact that teleconference through the telephone number. So I will give the telephone numbers is 04023680456. So once again I will repeat it, 04023680456. So this today live conference there are two experts will be there. There is a mathematics experts will be there here. So one is Professor K. Phaneendra, Professor of Mathematics, Osmania University, Hyderabad, and one more madam is there, Dr. K. Vijayalakshmi, Associate Professor in the Mallareddy Engineering College. So welcome you, sir. So today we are going to give the live teleconference recurrence relations, sir. So madam, can you give the introduction about the recurrence relations, madam?
Yes. Dear viewers, we have studied many counting problems and counting techniques like addition rule, fundamental rules of counting, addition rule, multiplication rule, then permutations, combinations, permutations with repetition, without repetitions, combinations with repetitions, without repetitions, and also we used one principle of inclusion and exclusion and Pigeon hole principle. These are all major counting techniques. Other than these, there are some cases where we can't use these principles. There this recurrence relation occurs. In the name itself, recurrence relation means suppose you have one term, second term is obtained from the first term, like that, and these recurrence relations are very powerful and frequently occurring technique
for combinatorial mathematics, that any method for solving them is bound to have considerable importance. In mathematics, recurrence relation is an equation according to which the nth term of a sequence of numbers is equal to some combination of its previous terms. And in continuous mathematics, you have differential equations. So in discrete mathematics, we have recurrence relations. In this lesson, we will solve the recurrence relations. We will study how a recurrence relation is formed and how to solve how to solve the given linear recurrence relation under given conditions. There are four methods of solving
recurrence relations. Now students, let us focus on what is a recurrence relation, how it is formed. Sir will be explaining.
Good afternoon, viewers and dear students. Recurrence relations, the modeling of the recurrence relation. A physical problem will be given for you, and if I mathematically model that problem as a recurrence relation, means the nth term is depends upon its previous terms, not only single term, maybe more than its previous terms, then it is called recurrence relations. See how it forms recurrence relation mathematically, how we can form the recurrence relation. So called this recurrence relation is also called as a difference equation. The word difference equation came from numerical analysis. In first year degree, you know differential equations. The differential equations may have exact solution, may not have exact solution. When exact solution is not available for that equation, then we go for approximate methods. So one of the approximate methods, numerical methods. When we solve differential equation by using finite differences, then it produces the differential equation transformed to difference equation.
So how to solve difference equation? Nothing but how to solve recurrence relation. First let us see the how to modeling where these recurrence relations occurs. One of the beautiful problem is Fibonacci numbers. The Fibonacci, the first letter F. So the Fibonacci sequence is taken as Fn equal to Fn minus 1 plus Fn minus 2. Fn is nth Fibonacci number. Fn minus 1 stands for n minus 1th Fibonacci number. Fn minus 2 stands for n minus 2th Fibonacci number. So, clearly this nth term depends upon its previous two terms. Okay. Then how it is modeled? The problem, this Fibonacci sequence or Fibonacci sequence 1 comma 1, 1 plus 1 2, 2 plus 1 3, like that. Okay. This Fibonacci numbers formed how? That is by using a physical example, rabbits. Leonardo Pisano, so called Fibonacci, he did experiment on rabbits. What is that experiment? A young pair of rabbits which are of opposite gender is placed on an island. A pair of rabbits does not breed until they are 2 months old. Means after 2 months, this pair of rabbits will give a birth to new pair of rabbits. So, after they are 2 months old, each pair of rabbits produces another pair each month. Then if I model this problem as a mathematically, it gives a Fibonacci sequence. Let us see how it formulates. Let us denote this Fn, F suffix n, by the number of pairs of rabbits, after n months. That small n stands for after n months. So, obviously what happens? F1 stands for what? Number of pair of rabbits after 1 month. Since we are placing a pair in the first month, so there will be only one pair. So, F1 value is 1. Okay. Similarly, F2 stands for what? The number of pairs of rabbits after 2 months. But what is our condition? After 2 months only the pair will give a birth to the new pair. Another pair. Exactly. So, F2 is also 1. So, these are the two initial conditions for the Fibonacci sequence. F1 value is 1 and F2 value is 1. So, let us see this picture. This pictorial representation will elaborate our situation. This first young pairs, and in the first month only one pair of rabbits are there, and there is no reproduction, only one pair is there. So, total pairs 1. Now, in the second month also there is only one pair. So, second month there is one pair. Okay. Next one, this is first month one pair and the second month is also one pair. Now, after the end of second month, definitely the pair will breed a new pair, that is another this one, reproducing pairs, right. So, young pairs totally in the third month reproducing is one more pair, and previously one pair is there. So, total number of pairs 2. Next one in the fourth one, same logic, applying the same logic. After end of the 2 months, again one more pair will be there, new pair will be there. So, totally 3 pairs. Like that, this is a pictorial representation of the birth of the rabbits, provided that the condition is after the end of the 2 months the new pair will come. Now, so using that concept, this after n months, to find the pairs on the island after n months, add the number of pairs on the island after previous month, that is Fn minus 1, and the number of newborn pairs which is equals to Fn minus 2. So, exactly after end of the n months, the sum will be Fn minus 1 plus Fn minus 2. It is the relation. Clearly, nth term depends upon its previous two terms. Yes, exactly, this is a recurrence relation, so called the difference equation. And this type of definition, that means this type of definition with these two initial conditions, F1 equal to 1 and F2 equal to 1, is so called Fibonacci sequence. So, this is the modeling of a recurrence relation. And one more example, the Tower of Hanoi. It's a beautiful problem. Tower of Hanoi, generally we play this at our child level. What are the thing is here? There are 3 pegs are there. And we have to on the first peg some discs are placed on the first peg, such that the larger size disc is placed at the bottom and it's a smaller one placed on it and it's smaller one placed on it, like that. Now, the problem is we have to shift all the disc on the peg 1 to the peg 2 in the same order. Following this condition, what is the condition? The larger size disc must be placed at the bottom of the smaller one. Okay. This is the Tower of Hanoi problem. Okay. And here, since we have to model again this as a recurrence relation, so terminology again, instead of Fn, now we have used Hn. This Hn denote the number of moves here. That means keeping this disc from one peg to another peg, it is called a move. So, Hn stands for number of moves needed to solve tower of Hanoi problem with n disk. How many disks here? This n stands for n disk. Number Hn stands for number of moves to place n disk from one peg to another peg. Then I have to form a relation to find Hn value. So let us start with on peg 1 we have n disk. First one on peg 3 pegs are there. Okay, on peg 1 we have n disk. So logically the larger size disk is placed at the bottom, isn't it, right? Then upon that we have n minus 1 disks are there, right? So we move these n minus 1 disks using our condition. So what is the condition? Larger size must be placed at the bottom. We move this n minus 1 disk to the peg 3 using how many moves? Hn minus 1 moves. Why Hn minus 1? We already denote this. What is this Hn? Number of moves to move n disk. Now we are moving how many disks from first peg? Only n minus 1 disk we are moving to third peg. In how many ways? Hn minus 1 moves. So already the larger size disk one disk is already on the peg 1. Remaining n minus 1 disk are placed on the third peg. The situation is like this. See, the 3 pegs are there, A, B, C. 3 pegs are there. These are the 3 pegs, A, B, C. On the first peg, we are considering to explain the problem, we have taken only 3 disks. Okay, to understand the problem, only 3 disks are taken, and B is the second peg, C is the third peg. What we did, the smaller side red color disk is placed, is moved to third peg, right? So no problem at all, the condition is satisfied. Larger side disk is still, green one is at the bottom, and the second disk, this white color is now it is moved to second peg, isn't it, right? Now again condition is satisfied. Now what is my aim? I have to move n minus 1 disk onto the third peg. So this red color disk is now moved to second peg, so that my condition is satisfied. Larger size disk, that is white color, is placed at the bottom. Now the largest one, that is the green one, is placed on the third peg, right? Now on this third green disk I have to place white one. So I have to move this red one to the peg A. Yes, it is done here, right? Next one, this BC, now place this white disk on the green one on the third peg. Now replace this red one onto the third peg. So all the pegs on all the disk on the peg A is shifted to third peg. See how many moves are there? I think almost 7 moves will be there. 7 moves only for 3 disks. To move 3 disks from peg 1 to peg 3, we need 7 moves. Okay. Now see, to formulate the relation, this is the theory. What I explained, the theory is here. We use one move to transfer the larger disk to the second peg, the largest disk. Then we transfer n minus 1 disk from peg 3 to peg 2 using Hn minus 1 additional moves. See, already here we have this Hn minus 1 moves are there to move n minus 1 disk to the peg 3, right? 1 Hn minus 1, and again from peg 3 to peg 2, again we are using how many moves? Hn minus 1 moves. Yes. Now my final optimal condition is what? All the disks on the first peg must be shifted to second peg in the same order. So totally how many moves are there? Hn minus 1, again Hn minus 1, so 2 Hn minus 1 and one larger disk, exactly madam, one larger disk, one move is for the second peg, that is plus 1. So the total number of moves Hn is taken as 2 Hn minus 1 plus 1, isn't it? Now again it is a relation where nth term depends upon n minus 1th term, right? Generally the recurrence relations, as you know, if somebody studied with multi-step methods in differential equations, numeric analysis, if nth term depends upon only single previous term, that is called single step method. If nth term depends upon more than one term, one term of its previous ones, then it is called multi-step method. So here also now this recurrence relation is called single step, because nth term depends upon Hn minus 1, whereas my Fibonacci relation, that is Fn equal to Fn minus 1 plus Fn minus 2, it depends on 2 previous terms, so it is called multi-step relation. Okay. Now how to solve this one? There are methods to solve recurrence relation. Substitution method is there, method of characteristic roots method, and method of undetermined quotients. These are the three popular methods, and one more powerful method, somewhat typical method, generating functions method.
Yes.
Okay.
Yes.
And since it is a recursive relation, can we solve this recursive relation recursively again? Means what? I know the recurrence relation. I resubstitute this recurrence relation again and again to simplify it. Yes, it is possible. Yes, for this problem it is possible. Now, this is my Hn, tower of on a recurrence relation, Hn equal to 2, Hn minus 1 plus 1. See, this Hn minus 1 again, this is Hn relation, 2 Hn minus 1 plus 1. Then if I replace Hn by n minus 1, what this becomes? 2 Hn minus 2 plus 1.
Exactly. Now this Hn minus 1 replaced here, isn't it? The simplification is here. Now again replace this Hn minus 2. Again, what is Hn minus 2 then? This is 2 Hn minus 3 plus 1. Again substitute here. Again I am getting this. If I resubstituting, that is called recurrence, recursively substituting my own recursive function, I will get finally this relation. What is this structure? 1 read from right side. 1 plus 2 square plus up to 2 power n minus 1. Like this. 1 plus 2 square and so on. 2 to the power of n minus 1. How many terms these are? This is 1 stands for 2 power 0. Right? Yes. 0 to n minus 1 means n terms are there. Sum of n terms. And what is this series? Geometric series. Isn't it? What is the common ratio? 2. Sum of n terms in a geometric general formula is what? Sum of n terms a into 1 minus r, r to the power of n minus 1 by r minus 1. Clearly here a value is 1, start the fundamental for 15. If n more number of disks are there, very typical. Yes. Right? Okay. This is so called tower of 1A problem. See, there is a puzzle, there is a clearly monks. In a long back ago, monks in a tower in a Hanoi city are transferring 64 gold discs from one peg to another one following the rules of the puzzle. Now see 64 na, then how many moves are required, and the condition is they move one disc each day. This is the condition. Yes. Isn't it? Right? Then how many moves are required? 2 to the power of 64 minus 1. See,
example, if you see 1 0 0 1, suppose you have only two variables, you will get 0 0 0 1 1 0 1 1. Suppose you have three variables, you get 1 0 0 1 0 1 1 1 0 triple 1 and then 0 0 0 0 0 1 0 double 1, like that. Here we have to find, suppose if there are n strings are there, means you have to form 1 0 1 0 1 1 0 0 like that, but here the condition is there should not occur consecutive zeros. So how to form this? Suppose an denotes the number of bit strings of length n without any two consecutive zeros. So to obtain a recurrence relation for an, note that the number of bit strings of length that do not have consecutive zeros, that will be either 0 or 1. Actually there should not be consecutive zeros, means at the end you should have 0 or 1. So we will assume that n greater than or equal to 3, because 2 it is not possible, we go for n greater than or equal to 3. So the bit strings of length ending with 1 without consecutive zeros will be obviously an minus 1. and if bit strings of length n ending with 0 without 2 consecutive zeros or the bit strings of length n minus 2. Suppose if it is ending with 1, you will be having another n minus 1 letters in that string.
Yes.
If it is ending with 0, there will be n minus 2. So, how you observe the recurrence relation for this? A n is equal to A n minus 1 plus A n minus 2 for n greater than or equal to 3. So, how to obtain initial conditions? We will take A 1 is 2. Why A 1 is 2? Only one string, it is either 0 or 1. The given condition is not is satisfied, which is not having consecutive zeros. Suppose if you take A2, A2 means, as I told before, you have 0 0, 0 1, 1 0, 1 1. So, we will have only 3, A2 is 3. Suppose if you want to find another, how to find the next terms with using with the help of previous terms, you can find A3. A3 is 5. You can calculate A4 as 6. Like that we can calculate, which is also satisfies with our Fibonacci series with A1 is equal to F3 and A2 is equal to F4. That means we will take An is Fn minus 2. This is one of the interesting examples in recurrence relations. So, how you define a recurrence relation? A recurrence relation for the sequence An is an equation that expresses An in terms of one or more of the previous terms of the sequence, say An minus 1, An minus 2, etc. for all integers n with the n greater than or equal to some positive integer n naught. A sequence is called a solution of recurrence relation if its terms satisfies the recurrence relation. The initial conditions for a sequence specify the terms that precede the relation takes that effect. Now, we will discuss about the order and order of recurrence relation. The order of recurrence relation An given by f of An minus 1, An minus 2, etc. An minus k, it is defined by k, where An depends on one or more of the previous k terms and k is the smallest such integer. A linear homogeneous recurrence relation of degree k with constant coefficients is a recurrence relation of the form An equal to C1 into An minus 1 plus C2 into An minus 2 plus and so on Ck An minus k, where C1, C2, etc. Cn are real numbers and Ck not equal to 0. So, if it is of degree k, kth term coefficient should not be equal to 0. Next is, for example, if you take An is equal to 3An minus 1 plus n square, which is a non-homogeneous recurrence relation of degree 1 and order 1. If you take the Fibonacci relation, the relation Fn equal to Fn minus 1 plus Fn minus 2, which is a linear homogeneous recurrence relation of degree 2. So, how you define recurrence relations of more degree? Suppose you take An is equal to An minus 1 whole square plus An minus 2 into An minus 3 into An minus 4, which is a homogeneous recurrence relation of degree 3 and order 4. Suppose if you take An equal to An by 2 plus 1 with A1 not equal to 0, it is a non-linear recurrence relation. Suppose you are given one sequence, let us find first few terms. See, first find the first 5 terms of the sequence defined by An is equal to 6 into An minus 1 with the given condition, initial condition A naught equal to 2. As sir told before, how to obtain the terms, second term from the first term, third term from the second term, like that. Suppose given condition is An is equal to 6 into An minus 1. How you find A1? A1 is equal to 6 A naught. Given condition A naught is 2, substitute this value. So, A1 is equal to 6 into 2, 12. Similarly, what is A2? A2 is 6 into A2 minus 1, that means 6 A1. 6 A1 already we obtained, which is 12. So, 6 into 12. Similarly, A3. What is A3? 6 into A3 minus 1. That is 6 A2. Substitute A2 value, which is 72, in place of A2. A4. How you find A4? 6 A4 minus 1, or it is 6 A3. Already we obtained the value for A3 in the previous step. So, 6 into 432, which is 2592. Similarly, A5 is equal to 6 into A5 minus 1, or 6 A4. Like this we will find.
Yes.
Okay. Now, one more example. Suppose how to apply these recurrence relations for real life situations.
Yeah.
When suppose on August 15th we will be decorating the flags, to hoist the flag, pole of a flag we are decorating the flag poles. For that, see here, find a recursion for the number of ways to arrange the flags on flag pole of n feet tall. N feet tall flag pole is there. By we use 4 different colors, different
Yes.
types of flags. Red flags, suppose we are keeping red flag means 2 feet high.
Yes.
White, blue, yellow, each 1 feet high. So, how to find a recurrence relation for this? Let an be the number of ways to arrange the flags on flag pole of n feet tall. If the first flag is 1 foot high, then there are an minus 1 to arrange the remaining flags. Suppose if you want to put first red flag, you have to take 2 feet high. So, the remaining feet are n minus 2 you have to decorate.
Yes.
So, how you obtain? See, there are 3 colors for the first flag. So, 3 an minus 1 ways to arrange the pole. In case the first flag is red, hence 2 feet high, there are an minus 2 ways to arrange the flags on the other n minus feet of the pole. So, what is the recurrence relation here? An is equal to 3 into an minus 1 plus an minus 2. So, students, you got an idea of recurrence relation. Now, we will solve the linear recurrence relation. There are 4 methods.
Yes.
First one is the substitution method. We can solve them by characteristic roots, generating functions and undetermined coefficients, which we discuss one by one. First, we solve the linear recurrence relations by substitution method. How, as I told you, one example we did by finding first 5 terms of the given sequence.
Yes.
Suppose if k is a constant, then consider the recurrence relation an equal to k into an minus 1 plus fn. Now, we will find the values recursively. First, we will find a1. What is a1? Is k a naught plus f1. What is a2? k a1 plus f2. Again, we substitute for a1. What is a1? a1 is k a naught plus f1. Like that, if you go on substituting, finally what you will get, see here, final answer is an is equal to k power n a naught plus sigma k power n minus r into f of r. So, this is the major idea behind solving the recurrence relation by substitution method. We'll let us see one example. Suppose you are given an, consider the recurrence relation an equal to an minus 1 plus f of n, where n is greater than or equal to 1. So, you find f of 1. What is f of 1? Or that means a1. a1 is a naught plus f1. Again, what is a2? a2 is a1 plus f2. But again, for a1 is a naught plus f1 plus f2.
F2. Yes.
So, substitute like that. a3 means a2 plus f3. Again, what is a2? a2 is a1 plus f1 plus f2. So, like that, if we go on substituting, we get an is equal to a naught plus sigma n equal to 1 to infinity fn. Okay. This is one general problem. Next one, we can apply to general conditions. See, look at one sequence recurrence relation which involves recurrence relation. an is equal to an minus 1 plus 1 by n into n plus 1. students start finding the values. What is A1? A1 is A0 plus 1 by 2. Again, what is A2? A1 plus 1 by 2 into 3. What is A3? 1 by 2 plus A0 plus 1 by 2 plus 1 by 2 into 3. Like that, if you go on finding An, your An is nothing but 1 plus sigma n equal to 1 to infinity 1 by n into n plus 1, which you can simplify 1 plus sigma n equal to 1 to infinity 1 by n into 1 by n plus 1, or you go on expand that sigma summation,
Yes.
which will give you 1 plus 1 minus 1 by 2 plus 1 by 2 minus 1 by 3 and so on. All the middle terms you will get cancelled and we are left with 2 minus 1 by n plus 1. So, this is the solution of the given recurrence relation an equal to an minus 1 plus 1 by n into n plus 1. I think this is the substitution method. Now, we discuss about solving recurrence relations using characteristic roots.
Yeah, method of characteristic roots method. This characteristic roots method is applicable to solve linear constant quotient recurrence relation only. Linear constant quotient recurrence relation only. Let me take one generalization. As madam said, the order and degree of the recurrence relation. Let us consider characteristic roots method. Characteristics roots method. If I consider a kth degree recurrence relation, means what? Nth term will be there, right? I will take C naught. C naught is a constant plus C1 a n minus 1 plus C2 a n minus 2 plus and so on Ck a n minus k equal to, see, using characteristic roots method we can solve constant coefficient homogeneous linear recurrence relation. Homogeneous means the right side value is 0 and this recurrence relation is valid from n greater than or equal to k. See, this is the degree of this is the last term a n minus k is there, no? That means this recurrence relation is valid from n greater than or equal to k and it is so called kth degree recurrence relation. Okay. Now, to solve this recurrence relation, since it is a kth degree recurrence relation, like in differential equations we have many equations are there. For example, if I write d square minus d into y equal to 0, homogeneous differential equation higher order, then what is auxiliary equation we write? Just m cube minus m square minus m equal to 0. This is f of m equal to 0, right? This is in differential equations. Likewise, to solve this recurrence relation, which is so called difference equation, kth degree, there is a characteristic equation represented by C of t equal to 0. One can say C of r also, okay? C of t equal to 0 or C of r equal to 0. Since it is the kth degree recurrence relation, is this first quotient C naught is as it is and write t to the power of k, kth degree, highest degree, plus this C1 into decrease 1 power t power k minus 1 plus C2 into t to the power of k minus 2 and so on plus Cn equal to 0. Now, where what is said? C naught, C1, C up to C, this is Cn are constants. So, it is a kth degree equation in t. So, it has k roots, it has k roots, isn't it, right? If all the roots, when k roots are there, like in differential equation, for example, auxiliary equation is having 2 minus 3 as solutions, for example, and 1, then what is the solution? We can write the linear combination of these, C1 e power 2x plus C2 e power minus 3x plus C3 to the power of x. Same logic here also. If k roots are there, for example, all the roots of this characteristic equation are distinct. For example, let me say k1, k2 and so on, kn, k, okay, already kth degree na. Let me take some p1, p2 and so on, pk. These are the roots, k roots which are distinct. Okay, may be real, may not be real, means may be complex also, does not matter. Okay, these are the values which are distinct. Then the solution of the recurrence relation, that means recurrence relation, here I have taken this nth term is required solution. So, this an is taken as P1 is the root, then corresponding term is P1 to the power of n plus. For the second root P2, C2 into, one can say, let me change, instead of P1 let me take alpha 1, I will take roots as alpha 1, alpha 2 and so on alpha k instead of P, generalization. So, this is alpha 1 power n, this is alpha 2 power n and so on, Ck, its coefficient if it is repeated 2 times. If it is repeated 3 times, alpha 2
We
is
will get a
repeated
second degree
3
polynomial.
Exactly, alpha 2 power n and its coefficient is second degree polynomial C3n, C4n plus C5 n square and so on. Now, remaining roots are distinct. Therefore, C6 alpha 3 power n, C7 alpha 4 power n and so on, like this. Only these two are the cases when the roots are distinct and when the roots are repeated. These two are the cases. Then now, here there is no case of exponential term here. Exponential solution is for differential equation.
Here
now,
no exponential
here the
terms.
solutions are the root power n. Okay, for difference equation, the solution is of this structure. Okay, for example, if I consider one equation, see, an minus 4 an minus 1 plus 4 an minus 2 equal to 0. This is what degree? Last one n minus 2. So, this recurrence relation is valid for n greater than or equal to 2. And what is the condition? When n equal to 2, the smallest value, this is a2 minus 4 a1 plus 4 a 0. So, to solve this recurrence relation, I need two conditions. Let us assume that a 0 equal to 1 and a1 equal to minus 1 to eliminate the constants finally. Right. So, what is this one? This is my recurrence relation. What is the characteristic equation of this first degree polynomial? This is the solution. Okay. Now, if I take this as 1, how many constants are there? C1 and C2, two constants are there and two conditions are given here, isn't it, right? So, if I substitute a 0 equal to 1, then what is this is when n equals 0, a 0, this is C1 into 2 power 0 1, that means a 0 value 1, C1 value is 1. Similarly, a1 I have taken as minus 1, right? So, this is a1 if I take C1 plus C2 into 2, that goes to, this is minus 1 and a C1 value I already got this as 1, 1 plus C2 into 2. So, value is what? Minus 1 by 2 equal to 1 plus C2, right? C2 equal to minus 1 by 2. So, minus 3 by 2 is the value. So, what is the solution? Now, this solution is called general solution. The solution is called general solution. Now, after getting particular values for C1 and C2, that solution is called particular solution. C1 value is 1 and C2 value is minus 3 by 2 into n into 2 power n. This is the answer. If one wants to check whether this solution is correct or not, just substitute my condition, put n equal to 0 here, n equal to 0. What happens? 1, this is 0, this is 2 power 0, 1. Yes, a not equal to 1. I am getting. Substitute n equal to 1. Substitute here 1. This was 1 minus 3 by 2 into 2 power 1. This is 2 minus 3 minus 1 by 2 into 2. 2 gets cancelled minus 1. Yes, my conditions are satisfied. Yes, this solution is correct. This is the way of solving homogeneous recurrence relation. What is this relation? Homogeneous recurrence relation only by using method of characteristic roots method, and the conditions are what? This conditions are, this is applicable only for constant quotient linear recurrence relation. The word linear stands for what? Here the terms are there, here these are the recurrence terms, they must occur at degree 1, all these occur at degree 1 and they do not multiply together, then it is called linear recurrence relation. For example, in madam said one example, something a n equal to a n minus 1 cube, right, plus 2. Yes, it is not linear due to this term a n minus 1 multiplied 3 times, right. So, it is a non-linear recurrence relation, Same logic, if I take like this, a n equal to a n minus 1 into a n minus 2 plus some 2 power n. Here also the terms are multiplied together, recurrence terms are multiplied together. It is also non-linear recurrence relation. And one more beautiful non-linear example is divide and conquer recurrence relation. Madam shown in a PPT. One example, a n equal to something 2 a n by 3, whatever it is, some 5 to the power of n, right. See this term, this a n by 3, this term is a non-linear term. It is that non-linear recurrence relation is named as divide and conquer recurrence relation, where this problem is occurred in computers, divide and conquer search techniques. Okay, divide and conquer in search techniques, this problem occurs. Okay, so we have to solve this non-linearity problem, we have to transform this non-linear into linear problem. Okay, now let us see the PPT. See, as I told you, this is my characteristic equation. Okay, you can say this is C of r equal to 0 instead of C of t, right. This is the kth degree relation, it has k roots. Okay, if all the roots are distinct, alpha 1, alpha 2, alpha n, all the roots are distinct, this is the solution, right. If any root alpha j, if we see alpha j is repeated how many times, this is p minus 1 means it is repeated p times, then this is the solution, generalization this. Okay. Now, this is one example, as I told you, a n equal to 2 a n minus 1 plus 2 a n minus 2. See, this can be written as a n minus 1 minus 2 a n minus 2 equal to 0. What is this one equation? Equal to 0, homogeneous, and it is a linear recurrence relation, and it is a constant quotient recurrence relation. Hence, we can solve by using characteristic roots method. What is the characteristic equation? C of r equal to 0, it is a second degree, clearly it is here, second degree equation. So, one can write r square minus r minus 2 equal to 0, exactly that is mentioned here. And what are the roots? If I mention these roots, r minus 2 into r minus 1 equal to r plus 1 equal to 0. So, roots are minus 1 comma 2 are the roots. So, obviously, what is the solution? C1 into minus 1 alpha 1 power n plus C2 into alpha 2 power n, exactly this is the solution. One can interchange this also, does not matter. Okay, this is the solution, and two conditions are given to evaluate the constant C1 and C2. Exactly substituting those two conditions, I am getting this A1 instead of C1 and C2, we have taken A1 and A2. These are the values of A1 and A2, and this is my final solution of this recurrence relation. This is a simple method, a very easiest method to solve homogeneous linear recurrence relation. Another one, see here equation is what? A n minus 6 a n minus 1 plus 11 a n minus 2 minus 6 a n minus 3 equal to 0, isn't it? Now, how many terms are there?
Characteristic equation is having more than 2 roots.
More than.
That means we will get a cubic equation, characteristic equation in cubic.
Now, see this relation here n minus 3 means it is the third degree recurrence relation. So, obviously, characteristic equation is what? R cube, here quotient is 1, R cube minus 6 R square plus 11 R minus 6 equal to 0. And the roots of this equation, cubic roots 1, 2, 3, all are distinct, right? When all are distinct are there, this is the solution. C1 plus C1 into alpha 1 power n, that is 1 power n, C2 into 2 power n, C3 into 3 power n. And how many conditions? Since 3 unknowns are there, we need 3 conditions, A0 equal to 2, A1 and A2 equal to 15. Substituting those 3 conditions, I am getting the value of C1 as 1, C2 as minus 2 and C3 as 2. One can do this algebraic manipulation,
Yes.
right? Simple calculations, elimination process, C1 2, C2 minus 2 and C3 value 2. Hence, substituting all the C1, C2 values, this is the solution of the recurrence relation. What is the recurrence relation? Higher order, higher degree recurrence relation, third degree. Okay. Now, the main part is, now is it possible to solve non-homogeneous recurrence relation? Yes. Non-homogeneous recurrence relation means, see, observe this, this one. This is the non-homogeneous recurrence relation where this f of n is there. Let me rewrite this. This is a n minus C1 a n minus 1 minus C2 a n minus 2 plus and so on C minus Ck a n minus k equal to f of n. The right side function, it is not equal to 0. This right side function not equal to 0, and this C1, C2, Cn may be functions of n or may be constants also, right? This f of n not equal to 0, it is named as non-homogeneous and constant quotient linear recurrence relation. Now, how to solve non-homogeneous recurrence relations? Like, then go for the non-homogeneous recurrence relation, get the solution and called it as particular solution, and the solution of the recurrence relation is taken as an equal to anc plus anp. This is the methodology to solve non-homogeneous. Now, this complementary solution, complementary function, and this one particular integral, already I explained complementary function, how to calculate ANC by using method of characteristic roots method. Let us see the particular, how to evaluate particular integral. This particular integral is evaluated by using method of undetermined coefficients, method of undetermined coefficients. Let me explain this. Yeah, see, for complementary function, this is my homogeneous recurrence relation. Okay, I will get the solution. That solution is called complementary. The solution of this one is called ANC. Then go for the particular integral. Now, this is the structure. See, this g of n, instead of f of n, we have taken g of n, right? And this structure, whatever this structure is there, let me explain this elaborately. See, now, the solution is here. Let us consider my problem as, my equation as an plus C1 into an minus 1 plus C2 into an minus 2 and so on, Ck into an minus k, nth degree equal to f of n. This is my equation. What is this equation? Non-homogeneous recurrence relation, correct? Now, like in differential equation, this right side function, if it is e power ax, we have some methodology. If this is sin mx or cos mx, some technique is there. Right, e power ax into v model, some technique is there. Here also that, right? When this structure is there, then assume that the particular integral a and p as, assume particular integral as, what is the method named as? Method of undetermined coefficient. Instead of known coefficient, put one unknown coefficient, let us say that as some d. D is not known for me now. D into a power n, such that, what is the condition here? assumption is this one. What is the condition here? If this a value is there na, here a value, a is not a root of characteristic equation, not a root of characteristic equation, C of t equal to 0. Okay. Now, when this is one, when second assumption.
Yeah, madam, good afternoon.
Good afternoon.
Non-recurrence, non-homogeneous recurrence relation and homogeneous recurrence relations. So, non-homogeneous recurrence relation should be changed as homogeneous recurrence relations, number 1. So, f of n not equal to 0 is non-homogeneous recurrence relations.
Yes.
Yes.
It is possible to we can change the homogeneous recurrence relations?
No, not changing, we are not changing. Methodology to solve non-homogeneous recurrence relation is like an equal to, it is a solution, it is the sum of the two components, sum of the two solutions. One is complementary solution, another one is particular solution. What is complementary? It is the solution of homogeneous recurrence relation.
Is it clear?
Okay.
Okay, thank you.
Now, assume then now if see here a is not a root, then this is my particular integral assumption. If a is a root of characteristic equation, a is a root of characteristic equation with multiplicity m, with a multiplicity m. What is multiplicity? Means repetition number. That means a is repeated 2 times, then m value 2, a is repeated 3 times, m value is 3. If a is a root of characteristic equation with multiplicity m, then assume the particular integral as a and p as d into n to the power of m into a to the power of n. Okay, these two are the assumptions. Then lastly, what we substitute this a and p, substitute a and p in recurrence relation, in non-homogeneous recurrence relation, and get the value of d. Exactly, get the value of d. Okay, this is case 1. What is the case 1 here? The function is of the form f of n equal to c into a to the power of n. Now, another case is there. Second case 2 is if my non-homogeneous, the forcing function, that is right side function, is of the form some d naught plus d1n and so on ds n power s. That means nth degree polynomial multiplied by a to the power of n. Okay. Now, again 2 cases here. If a is not a root of characteristic equation, a is not a root of characteristic equation, that is c of t equal to 0, then assumption for particular integral is this a and p. See, or in this function, these d naught, d1, ds values are known values for us. It is given in the problem. That means yes. 1 plus 2n minus 3n square, like that. Okay. Then in place of known values, put undetermined values. Say, one can say I will put a capital D naught, which is unknown, d1n and so on, ds n power s into a power n. This is the assumption, and substitute this a and p in the recurrence relation to get all the values of capital D naught, d1 and ds. Another case, same logic. If a is the root of the characteristic equation, if a is the root of characteristic equation c of t equal to 0 with multiplicity m, then assumption for a and p is, then let a particular integral be same as it is. These are the undetermined quotients d naught ds n to the power of s, and n power m is extra term. This is a to the power of n.
Yes.
Now, these two are the cases occur in this one. Let me clarify this this one by taking one example. The example is, let me take, generally I am taking this one, a n, like previous problem, minus 4 a n minus 1 plus 4 a n minus 2 equal to some 3 into, let me take, since 2 is the root, let me take 3 into 2 power n, 3 into 2 power n. It is a clearly linear, non-homogeneous, constant quotient recurrence relation. So, how to solve this recurrence relation? First, consider two ways. The solution is briefly I am telling this one. Solution is that is a n equal to complementary function a n c plus particular integral a n p. This is equation 2. Then how to calculate the complementary function a n c, right? Consider first, as someone is asking how homogeneous means, this a n c is the solution for homogeneous recurrence relation. Consider homogeneous recurrence relation of equation 1. What is that? A n minus 4 a n minus 1 plus 4 a n minus 2 equal to 0.
Already we find out.
Then the characteristic equation is what? C of t equal to second degree recurrence relation. So, 1 into t square minus 4 into t plus 4 equal to 2. So, the roots are 2 comma 2. So, 2 is a repeated root with a multiplicity 2. Therefore, solution. What is the solution? Complementary solution here.
1 minute.
Complementary
Solution.
complementary solution is a n c equal to c 1 plus c 2 n into 2 to the power of n. This is over. This is third. Firstly, the particular integral, that is a n p. Now see here, f of n is what? F of n is of the form
Thank you.
3
Thank
into
you, sir.
Time up, we will wind.
yeah.
Yeah. Thank you, sir. Thank you. Just now we find out the homogeneous and non-homogeneous and particular solution and complementary function solutions. So thank you, sir. Thank you for your valuable time.
Always
And
welcome.
thank you the viewers. I think you have understood whatever the DMS recurrence relations, how it is very easy to you. Thank you, madam, and it's very thankful to come to my studio and you clarified the some doubts, and maybe this video is useful for all the students who are studying BSc or MSc or it's any study level. This is a very easy things. Thanks once again. Thank you, sir, and thank you, madam, and thank you.
Thank you.